Today we are going to discuss about the output equation of DC machines. Okay, it is the first topic in the DC machine design. So normally the DC machines, in the sense, it have the two different parts and three different categories. So that is the stator as well as rotor, and apart from that it have the many types, many mechanical parts, that is the yoke as well as commutator, brushes, bearing, etc. Right? Then while you are considering the major design, that is the diameter and length, you need to consider that was the main dimension of the machine that you are going to design from the output equations, right? So it's have three different types, that is the sun motor, series and compound motor. These are the basic. These have three different categories. Before you are deriving the output equation of the DC machines, you should remember this all expression, that is the back EMF equation or EM induced EMF in the DC machines. EB, it should be equal to P pi NZ divided by 60A, whereas P is the number of poles, flux in Weber, speed in RPM, total number of conductor, that is Z, then the 60 is the constant, then number of armature parallel path, that is the small a. Then this all already we have derived in the last class itself, that is the AC, choice of specific electric loading and choice of specific magnetic loading. Then the flow of current IZ, it should be equal the current flow in the armature divided by the number of parallel path. So this all expression you should remember while you are deriving the output equation of the DC machines. If you are written this, it is very easy to derive this expression. Normally the power developed in the armature, it should be equal EB, that is the developed EMF into flow of current into 10 power minus 3 kilowatts. That is the power developed in the armature. Then you are substituting the EMF equations from that. You can substitute in the equation 1, that is the you are replacing EB into P pi NZ divided by 60A into IA is the then 10 power minus 3, the same you are substituted. Then again you are considering the speed in RPM, that is why the capital N, you are replacing it, that is the capital N divided by 60, that is the capital N is indication of speed in RPM, revolution per minute. While you are converting from minute to second, you can put divided by 60, that is why N divided by 60, the speed is RPS, that is the small n, that we can replace it N divided by 60. Then the capital N is the speed in RPM that I mentioned. Then similarly the I divided by IA divided by A, that we can replace IZ, right? So that we can replace it. After replacing these two expression, the equation 1 modified into like this, P pi N Z into IZ into 10 power minus 3, the equation 2, right? From the specific electric loading, from the specific magnetic loading, we can rearrange this expression again while we are substituting this value P pi as well as IZ and Z from these two equation, we can replace it. Then finally we can obtain the equation 2, we can replace like this, dAV into pi dL, that is the replacing P pi, then small n, that is the speed in RPS, then IZ into Z, that is the AC pi into D, right? We are replacing it. So while we are multiplying this expression, here you see the both term pi is there, T is there, so pi square D, similarly L, then dAV, AC and small n into 10 power minus 3, that was actual output equation of the DC machine. So we need to introduce the output coefficient, that is the C0. The C0 is nothing but, here we are considering this all constant value. This value is never it will be getting changed, because while you are designing the machine, they are giving the some values. That is the pi value you all know, that is the 3.14. Then BAV, that is the specific magnetic loading or average magnetic flux density. While you are solving the problem, they are directly giving you, right? Similarly, the total number of ampere conductor also, while you are solving the problem, they are giving. So this value is never it will be getting changed. So we are replacing into C0. The C0 we can call it as output coefficient. Based on this value, we can find it out D and L. The D is the diameter as well as length of the machine. That is the main dimension. While you are designing the machine, you should find diameter and length of the machine. For that particular case, you need to design this output equation, or you need to derive this output equation. So this output equation we can consider both motor as well as generator. For the case of motor, the PA it should be equal the output power, right? PA it is the generated power developed in the armature, it should be equal, that is the rating of machine or output power. Similarly, if you are considering the case of generator, the PA, that is the PA is the power developed in the armature or power produced in the armature, that is the generator. Because generator it can capable to produce the power, right? So the PA it should be equal P divided by the efficiency. The eta is the efficiency, that is the efficiency notations, right? So this is the output equation of the DC machines. From this output equation we can find it out diameter and length of the machine, that we will be discussing in the next session. Thank you.